this video, we're going to look at section 6.3. So as a reminder, in chapter 6, what we've been looking at is variable selection, and if we have a large number of variables, what this chapter is helping us learn to do is how to kind of narrow down which variables to include in our model. So as we perform variable selection, again, it's important to remember this isn't going to give us a perfect model. This is just guiding us and helping us, select what variables we're going to include in our model. So in this section, we're going to look at a new way to do this, and it's called the all possible regression selection procedure. So it goes on to say, now that we have more powerful computing methods, we can also do an all subset selection method, which gives limited output from fitting each possible model. This is more subjective approach than the stepwise regression. We can use quantities such as the highest adjusted r-squared, highest r-squared, smallest s, and a model with mallow CP equal to k plus 1 to choose the model. So notice what we've got here. So each one of these are all different criteria. So usually before performing model selection, you'll decide which one of these criteria that you're going to use. And what you'll find is different fields tend to use different criteria more often, or maybe depending on the type of data, you might choose a different criteria. But one thing that we want to be careful of is that we don't look at all of these different criteria and say, well, this one did this and this one did this and the second one was what I was going for, so that's where I'm going to proceed. We want to be very open and honest about our analysis and very straightforward from the beginning. So generally you'll choose which one you're going to use. Now that's not to say you might look at the output from multiple of them and say, hey, we see there's agreement for all of these, or there was disagreement. There is some choices that can be made there. So just to recall here that r squared is equal to 1 minus the SSE divided by the SS total. We also have here r squared adjusted. And so here we have our formula for r squared adjusted. And notice we could write this as equal to 1 minus n minus 1 in the numerator, n minus k plus 1 times the SSE divided by the SS total. All right, and so notice where this is coming from. You've got your MSE here, so all we're doing is pulling out the degrees of freedom from the MSE to write this in this form, and this helps us easier, or it makes it easier for us to see the relationship between r squared adjusted and r squared. So just a couple notes here. The r squared adjusted will always be smaller than the r squared. The reason for that is r squared is putting that penalty on having multiple variables in the model. That's where the adjusted comes from. If the SSE does not decrease substantially for additional predictors, the adjusted r squared value is much smaller than the r squared value. And then this measure is very useful to compare two or more regression models that use different numbers of independent predictor variables. And we'll actually see that later on in the notes. So let's look a little bit at the CP criterion. So the CP criterion is another useful measure based on the total mean squared error. And so they've abbreviated that here as TMSE. So we've got the formula here, so let's kind of pull apart a couple of the different pieces to see what's going on. So this piece right here, what this is this is the mean response for the fitted. And then if we look at this piece right here, notice this is the mean response for the truth. So you can see here we're looking at a difference we're looking at a measurement of the difference between those two. So if there's no bias in the regression model, then the mallow CP should be small or near the value of CP equal to P plus 1, where P is the number of predictors. We're going to choose a model with CP having values that are small, so that's our goal here. We want small values, indicating a small total mean squared error, and near P plus 1. And so this is a property that indicates that little or no bias exists in the subset regression model. However, due to the way that CP is defined, the regression model containing all of the potential predictor models will always have the value CP is equal to P plus 1. And we'll see that when we look here at the output. And then finally, another criterion that we could consider is what is called the press criterion. So the press, or also known as the prediction sums of squares, we've got the formula for it here. And what it's looking at is it's looking at the predicted value for the ith observation obtained when the regression model is fit with the data point for the ith observation when it's admitted from the sample. So in other words, we pull out each piece and we see what happens. So note here that small differences in yi minus y hat I, and notice that y hat I, that's the one with the ith observation removed, indicate that a model is predicting well, so we desire a model with small press statistic. So one thing to note here is for these different criterion will depend on if you want the value to be large or if you want the value to be small. And so we're going to look at an example. So we're going to go back to that example that we had at the very beginning of chapter 6. So before we do that, let's remind ourselves of that example. So going back in the notes, we are going to look at page 2. So we had this example right here. So recall for this example, we had 10 different independent variables, and our goal is to use variable selection to help us remember or help us decide which of these 10 variables should be included in the building of the final model. So again, we're not saying that we're going to select these variables and then we stop. We're just saying we're selecting variables and then using those variables, we're going to go on and build our actual model. All right, so we've got these 10 different variables, and we're going to see if we can figure out which ones we should consider when fitting our model. All right. So first of all, we're going to see how to do the all subset regression using Minitab, and so that's what we have right here. And so you'll notice up at the top, we've got the directions for how to do this in Minitab. Now you should have got an email from me with how to get Minitab on your home computers. If you didn't get that or you had any trouble with that, please let me know. And then here we have the output. So let's look at some different pieces from this output. So first of all, remember that the number of predictors that we have for this scenario is 10. And we looked at mallow CP a little bit ago. And remember that if we contain all of the potential predictors, mallow CP should be equal to P plus 1. Notice here, if we look in the mallow CP column, which is the most we could include, we get the mallow CP of P plus 1. So notice this is the number of predictors plus 1. So looking through here, let's kind of look at how to read this output. So what the all subset regression model or subset selection does is it starts out down here and it has all 10 variables. So notice if we look at this part of the output here, we have X's under all 10 variables. Next, what it then does is it says, okay, well, what if we're just going to include 9 of those variables in the model? So it looks at all of the potential combinations of 9 variables. And then what it does is it tells us the 2 best. And so notice here, if we go across, we see the 2 best that only have 9 is the one that excludes variable 7 and excludes variable 10. Next here, we've got all of the possible models that have 8 variables, and these are the 2 best. And going across here, we can see that the 2 best, one of them is the one that excludes variables 7 and 8. Oh, pardon me. Here, to make this easier, let's do this. To exclude nine and 10, whereas this one is going to exclude 8 and 10. Okay? And you could keep on going down, all the way down to where we look at all the possible models that only have one variable, and we see the 2 best are the one with the first variable and the 7th. All right. So here are those results in a table. And so these are the ones that have the results for the best. So if we look here, the model that has the that is the best, that only has a single predictor, is that model that has x1 in it. We see that it has an R squared of 0.619, adjusted R squared, MSE, CP, and press. And if we look here, if we go back to our output, looking at those models with one variable, we can see here that when we have x1 in the model, we've got an R squared of 61.5, and when we have 7, we've got an R squared of 69. So that's an obvious drop there. You could do the same thing with 2. We could compare this model with this model, and notice from R squared adjusted we go to 74.4 to 66.1. So that's where this table here is coming from. They're just choosing the best one out of those 2 rows. And again, remember that for some of these values, we want them to be high, and for some of them, we want them to be low. So for example, when we look at the R squared and the R squared adjusted, we want each of them to be high, but we want the CP and the press to be low. So make sure to keep that in mind when you're making these different comparisons. Now, usually what we do for any of the criterion, when we compare the different models going down this way, is we're looking for when things kind of start to level off for our different criteria. So for example, if we look here at our R squared, notice that as we add in the variables, we're seeing large increases in the R squared, but once we get up to here between 3 and 4, we're starting to see a leveling off. And we can see that here looking at the values as well. So what we would do in this case is once you start to level off for your R squared, you don't want to keep on tacking on more variables because you're not really getting high gains at that point. And we could do the same thing for any of our other criterion. Remember that we want R squared adjusted to be high, so we would again go this way. But for CP and press, we want them to be low. So we make the same kind of plot, but now we're looking for when they start to get low here. Same thing with the press. And so visualizing it this way can help me decide, well, which of these which of these models or which of these variables to include in the model am I going to work with? And so looking at this, more than likely our choice would be somewhere between the 4 and the 5 model. So we would pick one of these sets of variables because again, that's when we start to see for each of our criterion, we start to see that level off. And then one thing to keep in mind is that the variable selected by these criteria may not necessarily be the same. It's also been shown that none of these criteria are always superior to the others. So we should always compare residual analysis and experimental knowledge in determining the final model. So when we look at variable selection, it's not like there is this clear path and we always do X, Y, and Z and that gets us to our model. It's a bit of an art form. We have to take different things in consideration. We might look at different criterion. We want to be very careful though that we're not doing that in a way that we already had our model in mind and we're just making sure to justify it. We do want the data to tell us or to lead us to what we should do. But again, it's a bit of an art form. There's not this set path that you're always going to follow. And so that's why it's very important that no matter what you do, that you always very clearly document your steps and say, you know, these were the choices that I made. This is why I made these choices, so that somebody analyzing the data following you can follow your steps and know exactly why you did what you did. And then we've got one last page here. And so this is just some caveats. So looking overall at chapter 6, so you should not use the stepwise procedure or the all possible regression procedure to determine the final model and predicting why. Again, these steps are just helping you to find the variables to include in the model. These procedures conduct an extremely large number of tests, so the probability of at least one type 1 or type 2 error is going to be extremely large. Usually higher order terms are not included in the variable screening procedure. Therefore, the final model will be a first order model, which is usually not realistic for most real world relationships. So again, these models that we're getting here, you really want to think of them more as just helping you identify which variables to consider for your final model. And then even if higher order terms are used in the variable screening methods, most time the model chosen by these methods is nonsensical. Because of this, it does not result in a hierarchical model. And then make sure don't abandon your common sense when looking at variable selection. So some important variables may affect Y in terms of interacting with others, and this is often overlooked in the variable screening methods. Because again, we're not looking at interactions here, we're just looking at what variables to include. So as long as we use the variable screening method for their purpose, which is just, again, variable screening, most of these problems can be avoided. And then begin the model building phase, using what we saw previously in Chapter 6. So this concludes the Chapter 6 video.